a joint work I did with Avelio Sepúlveda from Santiago in Chile. And so what we were interested in this work is to look at continuous spin systems. So these are systems that live on a lattice. For most of the talk, it will be Z2, and from time to time, it will be Z4. And so those spin systems, they have a continuous symmetry group. And in some cases, there is what's called the topological phase transition that this system undergo when we vary the temperature. And we were interested in quantifying the amount of fluctuations that are due to the vortices. So I will introduce the vortices later. So let me introduce the models that we will consider. So there will be, as I said, spin models on the two-dimensional grid. And when we will consider the Z4 grid, it will be for lattice gauge theory. And so on this slide, I have 4 models that will be important in the rest of the talk. All of these models will equip the sites of Z2 with a spin. And on the left picture, the spin is a ±1 valued. And in that case, it's called the Ising model. If the spins take their values in the unit circle, this is called an XY model or a plane rotator model. If the spins take their values in the real numbers, this is the so-called Gaussian free field, which has been a main character of many talks so far in your seminar, I know. And it's in some sense, it depends on the way one looks at it, but in this setting here, it's the simplest of all because it's a Gaussian field. And the last character here, which is still a model defined on Z2, is the so-called integer valued Gaussian free field, which is the same as this field here, except the spins are conditioned, restricted to take their values in the integer Z. And so in all of these 4 cases, we equip the system, so this function from Z2 to their spin values here, with a Boltzmann measure or a Gibbs measure, and it has the same structure in each of these 4 cases. The probability of a configuration will each time be proportional to the exponential minus a kind of a L2 norm of the gradient between neighboring sites. And the beta here will be very important. It's called an inverse temperature. And what you can see here is that if beta is very, very large, the probability of a configuration which has large gradients will be very small. So beta very large is this picture here. The probability measure will be kind of concentrated on configurations that are very ordered. And this is why we said that beta very large corresponds to very low temperature, and the correspondence is as follows: beta is always 1/t. In the opposite regime, if beta is very, very small, you have something very disordered, and you get closer and closer to the uniform measure as beta goes to 0. So usually these systems, you have to be a little bit careful. You have to start with finite volume systems with some kind of boundary conditions, and then you let the boundary conditions go to infinity. This is sometimes a subtle business, but in this talk, I will be a bit fuzzy about those questions. Okay, so let me start with the first model in this line, the simplest, which is the Gaussian free field, and where the field may take any real valued number on each point. So here I have an n×n box in Z2. And this picture that I stolen from the web, maybe from Scott, I'm not sure, has the 0 boundary condition, a Dirichlet boundary condition. And as we have a quadratic form in the exponential here, it's obvious that we are in the presence of a Gaussian vector. And the first thing you may compute, for example, is the variance of the Gaussian random variable of the field that you have in the middle of your box. And it's easy to see that it has to do with the behavior of the random walk here, the green function here. And in 2D, the variance will scale like log of the size of the system. And the dependency in beta, in the inverse temperature beta, which is here, is very simple. it's linear in 1 over beta in the same way that the variance of the Gaussian variable is linear in sigma squared. Okay, so you see here that in this Gaussian case, at least the influence of the temperature is trivial. If we now go to a spin system which is not Gaussian anymore, but which has this discrete symmetry, the Ising system, when the temperature T is very large, it will be this window here. The system more or less looks like a white noise, and in a quantitative term, it means this region here will be exponentially, will have exponential decay of correlation with respect to that region here. So it's more or less a white noise besides some exponentially decaying terms. In the opposite region, if the temperature is very low, so here this picture, I think it's also stolen from the web, but I think was prepared with plus or black boundary conditions here. And the system remembers this boundary condition all the way to the bulk. And this is called symmetry breaking or long range order in physics. And in between, you have one critical temperature, which is known since Onsager. And at that critical temperature, you have something very nice with fractal curves and so on. Okay, so in the next slide, I want to very quickly tell you why a discrete symmetry that we have in the case of Ising gives you such a long-range order behavior when the temperature T is very small. And the reason I want to do it is that when we will switch to the continuous symmetry spin systems like the XY case, this argument will fail and long-range order will not exist in dimension 2. So for Ising, what is this argument? It's a very classical argument, which is called the Peierls argument. You imagine that you have an n-by-n box here with plus blue boundary conditions. And you ask yourself, what's the probability that by the time you reach the bulk of the system, for example, the middle point, what's the probability that you changed your mind and that this middle point here carries a minus spin? The observation is that in order to achieve that, it's necessary that somewhere you will find such an interface gamma, which will have plus outside and minus inside. So you may have one such interface, maybe 3, maybe 5, but you need at least one. And the point of Peierls' argument is to say that each fixed such interface gamma costs a lot in terms of energy, because all those edges will have a plus on one side, a minus on the other side. And if temperature is very low, it means beta is very big, and it will cost exponential minus beta. And so in total, the cost of one interface will be something like exponential minus beta times the length of gamma. And the conclusion of the argument is a combinatorial argument, which tells you that there are not so many available interfaces to change the phase from plus to minus. There are exponentially many interfaces with a certain exponential rate. But when beta is large enough, you can beat this exponential rate. And so it is getting very large, very difficult to pay this energy cost. So this is an energy versus entropy cost, which has the implication that there is this long-range order. I will not give more details here, but I will say in 2 slides why this fails for the XY model. So this is another picture stolen from the web, and this is a 500 by 500 grid, where all the spins in this 500 by 500 grid are equipped with the spin in S1, in this unit circle here. And they are colored in this nice periodic fashion, which is well known to computer scientists. So when the temperature is large, not surprisingly, and it's not difficult at all to show, you still have this flavor of white noise, in the sense that this region will be exponentially decaying from this region here. But now, when you let the temperature go slightly below, you start having pictures like that, and you still feel that this part of the space here is uncorrelated with that part of the space here, but maybe, and we'll see it is the case later, maybe one start hoping for some large-scale structures now. So why don't we have such a Peierls argument as we had before? In this setting, imagine we equip the boundary condition of this large n by n box with a east-oriented boundary condition. So we can ask ourselves, by the time we reach the bulk of the system, what is the probability that we will change our mind and we will now point towards San Francisco? So the big difference towards Jean-Christophe, I guess. So the big difference now is that it's no longer the case that when you do that, you will necessarily find somewhere an interface gamma, which will have east on the exterior and west in the inside. Now things are continuously moving. And if you want to do it in the best possible way in terms of energy, you can search among all functions from the spins to S1, what is the best possible function, and this is this one. It's called an harmonic map. In non-commutative settings, it would even be called an instanton. And such a function, you can compute the Dirichlet cost of this, the sum over all the neighboring I and j of the gradient of this function squared. And if you do this more or less by recurrence of the random walk, you will see that the whole Dirichlet cost of this is something like 1 over log n. So in other words, the energy cost is tiny. And because of those harmonic maps, which are sometimes so-called spin waves, it can be shown, it was shown by Mermin and Wagner, that the XY model does not have long range order at all. So for a long time, as far as I understand, in physics or maybe also in math, people thought that this system is not very interesting in dimension 2. Maybe it's a bit like Ising model in dimension 1. There is nothing much interesting to do here. But I once read an interview of Kosterlitz, who said that he was a postdoc of Thouless in the 70s. And Thouless showed to him simulations of liquid helium that were doing something strange at a certain temperature. The specific heat had some kind of non-analytic behavior, at least from the point of view of this experiment, and they were looking for a kind of transition occurring here. And they found one, and it's called the Berezinskii-Kosterlitz-Thouless transition. And what they found is that even though, even at tiny temperature, you will never have long range order, still there is this critical temperature here, above which you have this kind of white noise behavior, and below which you have something like that, which has power law decay of correlation, in the sense that the correlation between a spin, say here, and a spin, say here, will be polynomial in the Euclidean distance between those 2 points. And power law decay of correlation is something we like, is something physicists liked a lot in conformal field theory. For example, it's a sign of a critical behavior, of a scale invariant behavior. And what it meant is that all these models, all these temperature here, this continuum set of temperature below the critical point, must be related to some CFT, to some set of critical exponents, to some fractal properties maybe, or things like that. And another reason why physicists liked this transition very much is the fact that usually phase transition, they are second order, or they have they fail to be analytic if you look at thermodynamic quantities at the critical point. But here, for example, the free energy is conjectured to be C infinity. So it's not analytic, but you need very good eyes to spot that there is something going on exactly at that point. Okay, so let me say a few words on how they spotted this phase transition. And the argument goes as follows. So the probability of a configuration where spins take their values in the circle and the interaction is given by this Gibbs term, you can rewrite it very easily using trigonometry as follows. So it will be proportional to exponential beta, so beta is very important here, sum over the neighboring sides I and j of the cosine of the angle at I and the angle theta at j. And now it's very natural here to run a Taylor expansion of this interaction. And at second order, what it will give you is this quadratic cost between the angle at I and the angle at j. And this may remind you what we had at the very beginning of the talk, which was the Gaussian free field, where we had the sum over I neighboring j of phi I minus phi j squared. The -2 is there because Avelio told me that if I wouldn't put it here, people may think I wouldn't do Taylor the right way. So it's there, but when you have an energy profile and you shift it by a constant, it doesn't affect the Gibbs measure. So never mind the two. But if you stop your Taylor expansion at order 2, you may think the fluctuations here are given by a Gaussian free field. And in some case, it will be close to that when beta will be large, but it will never be exactly that. So a first reason why it's not quite like that is that those angles, they're in 0 to pi. They're not in the real number as we had before. A second reason is that in reality, what you would want to do is a fourth order term, sixth order term, and so on in the Taylor expansion. And one way physicists have been dealing with that is that they would run what's called the renormalization group analysis. And they would try to see how the terms in front of the quartic terms and so on would flow under the renormalization group in order to analyze this system. But there is a second way of looking at it, which is very close to what Kosterlitz-Thouless and also Berezinskii did, which is to think of this probability measure on the system, not quite as a probability measure on the angles, on the function on the vertices, but rather to think of it as a probability measure on the one forms, on what are the gradients, what kind of randomness you put on the edges of the graph. And I will not give a lot of detail, but if you now think of it as a Gibbs measure on the one forms, then if you remind your courses on differential calculus, I had to start from scratch because I had forgotten everything. But if you have some background on this, you know that those one forms, they may arise from zero forms, which are just functions that we like. But they may also not be exact. They may not always be gradient of a proper function on the vertices. And there may be contribution coming from the two forms via the co-derivative d star. And what happens is that in the case of the XY model, it's not completely correct, but in the case of the Villain model that I will introduce in 2 minutes, the contribution from the zero forms will exactly decouple from the contribution of the two forms, and those are called vortices. I'll get back to it. And so the fluctuation of this system here, which has a U1 symmetry, a unit circle symmetry, O2 symmetry, if you wish, this system, the fluctuation will come both from this zero form and also from those two forms. And in fact, the contribution coming from the zero forms will be exactly this Gaussian free field we've seen before. And in some sense, the whole point of the talk will be to ask ourselves what are the amount of fluctuations that are given by these two forms here. Are there questions? So now in 2 slides, I want to very quickly tell you how BKT found out about the transition. They had also energy versus entropy argument. And they said that as opposed to a spin wave, a vortex, a spin wave was this very slowly function that I had before. A vortex which winds around the singularity is something which is very costly on in terms of energy. And for example, you can compute that if you put a vortex here and an anti-vortex here, you can easily compute that the Dirichlet energy of this configuration here, which minimizes turning that direction here and turning that direction here, this Dirichlet energy will not be 1/log n as we had before, but now it will be constant times log n, where n is the Euclidean distance between those two. And so a logarithmic cost is something the system will not like, because in the Gibbs measure, it will be an exponential log n cost, and there will be the beta, so it will be exponential beta times log n. And so when beta will be very large, you will not have the room to put such vortex anti-vortex at far distance. And so the argument of Kosterlitz-Thouless is that when beta is very large, even though they are very costly, you will still have pairs of vortex and anti-vortex that will be close by. And as the temperature will grow, as beta will go to smaller values, suddenly the vortex and anti-vortex, the entropy will make them unbind, so they will kind of separate from each other. They will become free, and this is called a plasma. and the plasma is responsible for the exponential decaying of correlation. Okay, and at that point, when I started being interested by that story, I had the following completely wrong intuition, which I give to you. I thought, okay, when the temperature is large, there is a plasma, there is exponential decay of correlation, but I also thought that below the transition, because of this binding of positive singularities and negative singularities, the large-scale fluctuation would not see those vortices and would only see the background Gaussian free field. So I thought that vortices would only start contributing when they would go into the plasma phase. And in fact, this is a wrong intuition, and people knew this way before Avelio and I looked at it. So, for example, in this paper by Rosset, Kadanov, Kirkpatrick, and Nelson, which was very influential in 1977, they run two approximations of this system. And in both cases, they looked at the Lyon model, which is not quite the XY, and I will introduce just after, but just to tell you that back in 1977, the Lyon interaction was already something important. And so for this slightly different model, which still has the same O2 symmetry group, they understood that at large scale, it would look like a Gaussian free field, except you would need to slightly change its temperature. The Gaussian free field will have a slightly larger temperature because of those vortices. And the Migdal approximation scheme that they had gave a certain value, but careful renormalization group analysis, which is the second part of their paper, gave this precise prediction on how you would need to shift the temperature. It's called an effective temperature, in order to capture both the Gaussian free field and also those two forms, those vortices that fluctuate in the background. Okay, and remember this exponential minus pi squared over t that is here, or same thing, this exponential minus pi squared beta. And later on, Fröhlich and Spencer, they made a conjecture which is closer to the type of object that we are now using a lot in probability theory, in Gaussian multiplicative chaos, for example. They conjecture that if you view the Lyon field as a complex random field, so you view the spins in S1 as complex numbers in the plane. So this is a random field with values in the complex numbers. They conjecture that at large scales, it should be exactly like the complex exponential of the Gaussian free field, which is called complex Gaussian multiplicative chaos. So there was a talk by, well, there were a few talks I've seen in the lab about either Gaussian multiplicative chaos or even this complex Gaussian multiplicative chaos, for example, by you and now. Okay, so at the time in the late 70s and 80s, they knew that vortices, even at low temperature, they do contribute to the fluctuation of the system at large scales. So now in this slide, I want to briefly explain why we will switch from the XY model that I started with to this slightly different model, which is called the Lyon model, and which is very convenient for many reasons. So let me motivate this Lyon model. The XY model, I recall it was defined like that. The probability of a configuration of angles was proportional to the product of all neighboring sides of this exponential beta times the cosine. So just to recall things, if beta is huge, you want theta I and theta j to be basically aligned to each other. So now let me draw the function exponential beta cosine of theta as a function of the angle theta. It looks like that. And when beta is huge, it's going to have huge peaks near 0, near 2 pi, and so on. It's 2 pi periodic, so you may look at its Fourier mode, and those are well known. There's the case-modified Bessel functions, but at least to me, they're not so pleasant. They're a bit, say, complicated to work with. So at that stage, a natural idea is to say, okay, this interaction, which says how spins are interacting with their neighboring sides, let's take a simpler 2 pi periodic function. And a natural idea for this is to do, as we did before, a Taylor expansion of this exponential beta cosine. And as we've seen, the Taylor expansion is kind of this exponentially decaying term. But if you would not do anything, you would have this function here, exponential minus beta times theta squared. And it's not 2 pi periodic. So to have something that has to do with angles that are defined modulo 2 pi, it makes sense to add up all these Gaussians, which corresponds to this sum here, which is adding all the 2 pi periodic Gaussian. And this is sometimes called the periodized Gaussian. Why is this good? Well, if you compute the Fourier coefficient of this new interaction function, what you end up with now is something which is much simpler than a case-modified Bessel function. By Poisson formula, or just by direct computation, you get this Gaussian behavior, behavior for the Fourier modes of this interaction. And just notice one thing here, which is that the beta, which is always in the numerator in statistical physics, once you do this Fourier transform, the beta is now in the denominator. And later on in the talk, this will correspond to an inversion of temperature. Before going to the Fourier analysis, we will have the standard large beta is a small temperature, but after Fourier inversion, after this duality, we will change the temperature. And I'll get back to it at different moment, but this is the reason in this slide. Okay, so why do we want to go to the Villain model? Me, because I prefer Gaussian than case-modified Bessel function, but the true reason is that when you take the Villain model, this field here, this Villain field, in fact, exactly decouples into a Gaussian free field and something that lives on the two forms, and this will be what is called the Coulomb gas. And this thing here, those are exactly independent of each other. If you were to take an XY model, it would not be the case, and the interpretation of vortices would be slightly less clear than in the Villain model also. So as Kadanoff et al. Did in the 70s, and we will stick to the Villain model. The work by Fröhlich and Spencer that I will mention later actually works for both models here. Okay, so let me first define what is this Coulomb gas, and this will be the first result in this talk. So the Coulomb gas, maybe in this audience, I didn't quite kept track of who is there, but in case Sylvia is there or Paul also is there, the Coulomb gas in the continuous setting would be a very natural model in the setting of random matrices, for example. And so this is a picture stolen from Balin-Virag, I think, in the case of beta equals 2. And I will not go into details, but just think of random points in the plane that are confined to a disk in the plane because of a quadratic potential, and they repel each other with log interactions. What we will have here is almost the same thing, except we don't need to confine the particles. They will live in a finite n by n box. Technically, the box is the dual of the box on which the Villain is defined, because we have two forms, but never mind, it's not crucial for later. And this Coulomb gas has been studied a lot in the physics literature, for example, by Fröhlich Spencer, but also by Nienhuis, because it has many connections with many 2D statistical physics and all those works here. And the Coulomb gas that we have here is a two-component Coulomb gas. It's even a Z-component Coulomb gas, in the sense that on each side of this grid, we want to put an integer, Q at that point. And we look for a probability measure which will be defined on this integer valued field. And this is not going to be the integer valued Gaussian free field. Here, the probability of Q, which is assigning integers at each x of this lattice, will be proportional to this Gibbs term, exponential It's almost minus beta. There is a bit of 2 pi, but never mind this. But the difference with the Gaussian free field is the quadratic form. It's not the quadratic form given by the Laplacian, but it's the quadratic form given by the inverse of the Laplacian, and this is the reason for the log repulsion that you have between the Coulomb particles, which is exactly the same log repulsion that you would have in the continuous setting. And so the question we ask with Avelio is, can one have quantitative bonds on the way this field fluctuates, this Coulomb gas fluctuates? And so here is the result, but before I comment on it, let me say that in this continuous setting, for example, in those works, the way these systems fluctuate is extremely well understood. They know that the energy, the energy potential induced by those charges, which is this convolution of the charges by the Green function, or the Laplacian -1 of these charges, then this is the natural object to look at, and they know that this object fluctuates like a Gaussian free field, and they know the dependency in the temperature. They know everything. The dependency in the temperature is also 1/beta. So what we can show here is the analogous result, except we have a kind of 2-component setting, or Z component. So this would be the analog maybe of this work by Leblay, Sarfati, and Zeytouni. And in these 2-component continuous setting, as far as I understood, they have much less control on the fluctuation of the system. And in this discrete case, we will have some control, and here is the control. So we can show that the fluctuation, in the sense of the second moment of the variance, when we integrate this electric potential against a test function G, which is reasonable enough, the fluctuation, the variance of this will be what you would have for a Gaussian free field. So this is good. This matches with the continuous setting. But the dependency in the temperature is very different. It's very nonlinear in beta. And so what we can prove as a lower bound is something which matches with the results I stated earlier, which are these precise renormalization group predictions from Kadanoff et al. So if you wish, in that sense, we have matching lower bounds with those works in renormalization group, but our proof will not be perturbative at all. There won't be any renormalization group here. Another very important work, in fact, more important, because this is the direction that have proved the existence of the KT transition, is to have upper bound on those fluctuations. And that was done by Fröhlich and Spencer in '81. And they have those type of upper bound on the fluctuation, and those two bonds are not matching, and I will get back to it. So the next slide is the same kind of result, except I will give something about the Fourier transform, the characteristic function, which is the type of object you would want to control if you would want to prove a convergence towards a Gaussian free field. So the conjecture is that this field in the scanning limit behaves like a Gaussian free field, but with a very tiny constant, with a very small temperature. Sorry. And so in Fröhlich-Spencer, they proved a lower bound on those characteristic function with those estimates here. And what we show is upper bound. But here we do not have a matching bound with what we conjecture is the truth, which is this Kadanoff et al. We have a missing 2 here. And the comment I want to make is that the result of Fröhlich-Spencer, in fact, holds whatever the test function G is. It's completely true without any assumption on G. And the important comment is that any upper bound that you may look for cannot hold whatever G is, because if it was the case, it will rule out the KT transition. So for example, if G is a certain one form, which is well chosen here, the upper bound cannot be exponentially decaying. So the upper bound in that sense is a bit subtle, because it needs to be true only for a certain type of functionals. And for example, the 2-point function here, for that one, it is true. I will not say more about this, just to say that a consequence of this result is that it gives a lower bound on the correction that one has in the Fröhlich-Spencer work, which is this estimate here. Okay, so that's all what I want to say about the Coulomb gas. I want to tell you about another side of the story now, which will be the bottom of this diagram. And the bottom has to do with the Fourier transform of the Villain model. So what you do, so it's less easy to visualize in terms of probability. Here we have an exact decoupling. Here it's through the Fourier transform. So if you Fourier transform the Villain model, you naturally end up with something which is a random field on the two forms. So this is a random field on the faces of this graph, which if it was an n by n square, it's still more or less an n by n square. And so now you have an integer valued Gaussian free field on the faces of that graph, except, as I commented before, the temperature has changed. If here you have something which is very low temperature, by Fourier transform, the model in this dual world will be at very large temperature, will supposedly fluctuate very much. And if you want to make sure that the diagram kind of commutes, you can check that indeed there is a relationship between the Coulomb gas and this, either by direct Fourier computation or Riemann theta function. Okay, so what I want to do now is that I gave you results on the fluctuation of this system. Now I want to give you quickly corollaries on the fluctuation of those systems. So let me quickly define what these are. So I've stolen the picture from the work of Eyal, who is here, and Martinelli and Sly. So actually I stole it in their paper, but this simulation is a simulation for the restricted SOS model, not the integer valued Gaussian free field, but this is the picture I liked the most. So I'm sorry, but you should picture a field that takes its values in the integers, and this is a kind of large deviation picture for a slightly different model. Otherwise, it looks a bit more like they call it harmonic pinnacle. Anyway, so the probability measure on those functions that are on this n by n grid and take their values in Z is exactly the same as for the Gaussian free field, except two differences. First, the beta was in the numerator and is now in the denominator. This is this temperature inversion. And second, very important difference, the values of the field are restricted to live in the integers. Okay, so it's not Gaussian at all anymore because of this conditioning. And now I can state the result of Fröhlich and Spencer. Their goal was to show this intriguing phase transition, which is called the topological phase transition, and to show this change of behavior for the XY or the Villain model as the temperature drops. The difficulty here in such a system is that there is no long-range order even at low temperature. So in some sense, the idea of that proof is to go through the dual model to this integer valued GFF, because here there will be a phase transition. There will be a long-range order at low temperature and no long-range order at high temperature. So if you wish, the advantage of going through this dual picture, through this Fourier transform the model, is that now we do have a drastic change of behavior, a long-range order in one case and no long-range order in the other case. And in fact, so this high temperature Villain model will be mapped to a low temperature because of this temperature inversion, a low temperature integer valued Gaussian free field. And here, if you prescribe your boundary condition to be 0, in fact, you can run a Peierls argument a little bit like the one I explained to you for the Ising model. And it's not very difficult to show that when beta is, so in this notation, when beta is very small, because it corresponds to 1 over beta here, then the random surface has big difficulties to fluctuate, and it's called localization. It's basically flat with tiny fluctuations here. So this is not too difficult, but the theorem of Fröhlich and Spencer is to show delocalization of this random surface. In fact, in a strong sense, because by itself, delocalization is not sufficient to get back to the KT transition. But that is the idea. So they show a delocalization. The variance now goes to infinity logarithmically. So that's the result for just the second moment. So you see here that it's more or less like a Gaussian free field, but there is a correction epsilon beta on which I gave a lower bound in the previous slide. And the consequence of going through this dual model is that they obtained power law decaying lower bounds on the two-point function, which proved a KT transition for XY or Wheeler model. Okay, so what are our results on this integral value Gaussian free field? So this is something that has been studied a lot. So for example, Lubetsky, Martinelli, and Sly, they understood extremely precisely the fluctuation of those random surfaces when their temperature is very low. So when it's hard for them to fluctuate, they know exactly up to ±1 fluctuation where is the maximum of those fields. If the temperature now is large, so which corresponds to the Wheeler model to low temperature, which is the interesting phase for us, Matteo Verse has proven that the maximum will be at least as high as a constant times log n, a bit like what you would have for the Gaussian free field. And so the result we show is the opposite. We want to show that the maximum doesn't go too far. It's easy to show that it cannot go above what you would have without conditioning the field. So it cannot go further away than what you would have with the normal Gaussian free field. And with the normal Gaussian free field, you know that the maximum of the GFF has been studied deeply in the last 15 years by many, I will not cite them all, but lots of people. And so here we restricted the field to live in the integers, and we can prove much less than what, for example, Biskup and Wieder did for the Gaussian case. But we can show that the maximum lives strictly below the constant of the Gaussian free field, and there is this influence of the vortices here. So the max of the Gaussian free field would be here, this would be log n, and the integer valued is slightly below because of the vortices somehow. And we can also get bounds on how the free energy of this system behaves. And if you know how free energies are behaving, in this case, things are, well, no, let me not comment on this. So here on the sides of the free energy, we also have this Kadanoff et al. Bond, this matching bond. Okay, so to close the diagram, I gave you a result for the fluctuation here. I gave you a result for the fluctuation of this system. Let me just finish before giving some ideas of the proof on the fluctuation of this system here. So the result we can prove is the following. So we can, I stated already that Fröhlich and Spencer proved the lower bound on the 2 points correlation function. What we have is an upper bound. So previously there was a very important upper bound by McBrien and Spencer, which was the same as that, but without the vortices. It was saying that the 2 points correlation function is smaller than what you would have with a proper Gaussian free field. What we add to the story is that vortices do matter at macroscopic scale, and they matter this much. And here we have the same factor of 2 that we think should not be there, but we are lacking of ergodicity. We don't have this term in free energies and variances and so on, but when we exponential those, we lose a bit. And let me comment that this type of result is related to a very interesting work of Dario and Wu, who are both very much related to New York, at least to NYU, where they did a work for the Wheeler model in dimension 3. And what they obtain is they obtain that the 2 point correlation function is asymptotically as what you would get for the Gaussian free field, but with a correction. So they have estimates on the effective temperature, but in 3 dimensions, in some sense, lower and upper bounds, they are matching. So it's nicer in that sense. Okay, so in the rest of in the remaining time, I want to give you some words on the proof, and at the very end, tangential story, but depending on the time, the tangential story will be maybe just 1 minute. So how does the proof work? The main idea is as follows. So the probability measure of the Villain model is given by this. It's a product over the neighboring sites of, previously we had exponential minus beta cosine, but remember that I took a periodized Gaussian to approximate that, to slightly change the model. And so we have this periodized Gaussian now that lives on each edge. The main idea, in some sense, of the work is that here, those integers are just there to make the Gaussian periodized, and they are kind of averaged out in the partition function. The idea, in some sense, of this work is to promote, to give more values to these integers values m, and to promote this to the whole of a true random variable whose fluctuation will be important and useful. So we kind of extend this probability measure to a new probability measure, which is now not only on the angles theta, but also on these integers that live on the edges. So now this thing here will be a random one form that lives on the edges of the graph. And so this coupling of the theta and the m is given by what we have above. I just rewrote it as a gradient of the angles along the edges, plus those random integers on the edges. So I just kind of rewrote the probability measure, and I gave more emphasis on this one form m. And the next observations are the following, and I will give a picture after, that now when you view things this way, you can ask yourself, what is the law of this random one form m given the values of the angles theta? And this conditional probability measure, due to this product structure here, is still going to be a product measure here. And so you can interpret this law on the one form, conditional, you freeze the angles of the Villain model. And what you end up with, I'm going too fast, but I say in words, what you end up with is a product of integer Gaussian that live on the edges. They're independent of each other, but there is some quench disorder which is still given by this gradient of the angles on each of these edges. So in other words, the quenched law of this one form is simple. It's a product of integer Gaussians that are shifted. And the good news is that the curl of this m, or the differential of this m, is exactly a Coulomb gas. So in the next slide, I will just repeat things by saying that this framework gives you an algorithm, gives you a fast way to sample a Coulomb gas in dimension 2. So I just repeat the same thing, but with the notation I had before, which is this triangle Villain field here, Coulomb gas on the top here, and integer valued field on the bottom. And the idea to understand those fluctuations is to run this kind of new algorithm to sample the fluctuations of Coulomb, to sample the Coulomb gas, by considering this coupling of theta and the one form m. We first, in the algorithm, we first sample a Villain field with a Glauber dynamics, say. Then we sample this random one form quenched in theta. And then we get the Coulomb by taking the curl to go from the one form to the two forms. And why do we get something out of it? So the law of the one form m is simple. As I said, it's a product of independent integer Gaussian. So on each edge, you have an m of e, of that edge e, which is an integer Gaussian. So it's a kind of Gaussian, but it's restricted to the integers. The slight complication is that this integer Gaussian has a kind of mean, as a shift, which is given by the gradient of the angle here with respect to the angle here. So you have a kind of a white noise of integer Gaussian, but this white noise is shifted due to the quenched disorder. And what we claim is that out of this kind of white noise of integer Gaussians, we extract a lot of fluctuations on the Coulomb gas. But then what we can ask ourselves is that the fluctuation of the Coulomb gas is given by two sources of the randomness. One is the quench theta, which does fluctuate. And then condition on the theta, there is all the randomness given by those one forms. And we may play with both to try to optimize things and really understand the amount of fluctuations here. And just in a few words, if you want to optimize things, we first need to optimize how the quench disorder is behaving. And here, there is a new kind of spin wave that naturally enters the system, which is not the spin wave we had at the beginning of the talk, which was interpolating between Est and then West. It's not also the spin wave that is doing a vortex and anti-vortex that we had in the middle of the talk. It's now the kind of the harmonic extension of having an angle at pi over 2 and a neighboring angle at minus pi over 2. And in some sense, this optimized, this spin wave enters into the story and gives us, without running into any renormalization group, this term that was obtained by Kadanoff et al. Okay, so I will not say much more than that. I want to tell you very quickly the following, that in fact, this way of measuring the fluctuation of vortices also extends to the Abelian lattice gauge theory. So in a few words, here we have a Z4, and on each edge, so now the randomness will naturally live on the edges, not on the vertices. We equip each edge with a spin which will live also in the unit circle or in the U1 group. It's the same. And now the Gibbs measure is almost the same as what we had before, but it has some gauge invariance. The measure now is a product over all faces, not over all edges. So we shift things from the 0 forms and 1 forms to the 1 forms and 2 forms. It's a product over all plaquettes or all faces here, F, of in the classical case, it would be an exponential minus beta cosine. Here it's a periodized Gaussian for our work. But what you do is a curl of the theta, so it's a differential of the theta. But on each plaquette, you don't want to have too much fluctuation in some sense. And this gives you a well-defined Gibbs measure on lattice gauge theory with this abelian group. And there were many works lately by Chatterjee for the case of easing spins on the edges, or finite group by Forsström, Lenels, and Bicklund, and Sky Chao has done all finite groups, Abelians or not. And in some sense, what we do here is an extension to the continuous groups, but they are Abelian, so it's a U1. And what we look at is, as in all those works and in all works previously in the math physics about lattice gauge theory, is to look at this gauge invariant observable, which is natural from the physics point of view, which is to integrate the randomness on the 1 forms along this path gamma here. And in the 80s, Alan Guth and Fröhlich-Spencer, they proved that there is a very beautiful phase transition for the behavior of this Wilson observable, which has the same flavor as the KT transition in dimension 2. It doesn't go from exponential to power law decurve correlation, but it goes from area law to perimeter law. But I will not go much more into details. But the result that we can show is Alan Guth or Fröhlich-Spencer would give you a lower bound on the Wilson observables, and with our techniques, we can extend the previous work to this Abelian lattice gauge theory by showing that the Wilson observable behaves like a spin wave, like a Gaussian free field, which would be this term here. But on the top of this, vortices also add to the fluctuation, and here vortices are, in some sense, things that live on the 3 cells of the graph. and we get something which has the same structure as we had before. And there is a duality which gives the same, exactly the same as in dimension 2, exponential minus pi squared beta. Okay, so I think I had a second part, but this was just clearly way too much. So I will stop here. Thank you.
Thank you. So questions for Christophe?
Don't hesitate. I'm very happy if it's interactive. So even if it's very naive.
I have a question on the, let's say, on the considerations on the beta size and the transition points that I think was leitmotif in your presentation for some of the slides. And the question is, I saw in one of the slides that it looks like a real peak up and down when the temperature changes from cold to warmer to heat, higher heat. So I can see in that slide. The question is how beta determines that transition point. Is that like a real change in direction, or is that like a saddle point? It's a visible maximum, a relative maximum that is quite remarkable, or beta, which is
okay. I think I see what you mean. So
yeah.
So I guess it's not quite like in the 5-4 model where you have the double wave, and at some point you may start. So there may be some links with that, but as far as I understand, the critical beta has to do with 8 pi. So in the original works, you can exactly compute this energy versus entropy cost of the vortices. And you can guess some 8 pi phase transition, but this would be true for a Coulomb gas with very low activity Z. And as far as I understand, for the true XY or Lyon model, the actual critical temperature will not be exactly this 8 pi, and the Lyon and the XY won't have exactly the same critical point. And the exact value here, as far as I know, should be close to 8 pi, but it's not known. There is no exact conjecture for this T BKT in neither of these two models, as far as I know. And it's not like Onsager computation for Ising, for example. So,
right. The other question that I had is on the vortex. Like you called that the vortex influence is visible much more when in the Coulomb gas issue. That is more remarkable when it becomes like a plasma, when it's in interaction with the anti-vortex. It actually disperses. I think that's what they were used, and then it becomes like a plasma. But before that, I'm trying to relate this to the Coulomb laws. And can you expand on that? Why the vortex is not so significant by that's influencing the lower temperature, but until it becomes a plasma?
No. So I think what I meant is that they are not so significant below T BKT in the sense that they don't provoke this exponential decay of correlation. Okay. In that sense, they are not so significant, but still they do affect the critical exponent because they do induce fluctuations at macroscopic scale, which is in some sense what we proved rigorously, that it is strictly far from what you would have with the Gaussian free field. So they do impact the system, not by much because it's exponential minus pi squared beta, but they do impact.
Okay. Good.
I have a couple of questions. Thank you, first of all, for a great talk, Christophe, and congratulations on the wonderful results. So the first quick question is, Feulich-Spencer also applied to SOS, right? For this, so do you get the same results for that as well?
No, it's a very good question. So indeed, in this whole talk, I went only in the Villain model, and what we used deeply in our proof is this exact factorization property here, and this is key in our work. And so our work does not work at all at the moment, but I'm not so sure it will easily work in that case. It does not work at all for XY. While in the Fröhlich-Spencer result, let me go to the right slide. In the Fröhlich-Spencer results, in some sense, the story in the other side of the picture by this duality through the Fourier transform here. And their proof is more robust for the lower bound of the fluctuation, in the sense that if you need to work with those case-modified Bessel function, it's a bit more of an headache, I suppose, but you can still do it. And those case-modified Bessel function, when K is very large, they're very close to an SOS model. That's the way I understand the story. So working in that side of the picture works better for Villain than XY, but still works for the XY model by some more struggling. Our proof really works on this side of the picture and then extends the fluctuation to this model here and to this model here, but doesn't use at all the technology that Fröhlich and Spencer used. So it does not work for SOS model. Of course, the result should be true, but it does not work. And for example, the Coulomb gas in the case of XY is also there, of course, but is not as clear as in the Villain case.
Okay, the other question that I wanted to ask is, now sticking with the integer valued Gaussian free field, did you try getting a law of large numbers for the maximum?
What do you mean? You mean a CLT, or because
to get so I'm not sure, but just to get the existence of a constant before the log.
For the maximum, I see. Is here?
You cited exactly this.
So maybe what you ask is if we would want, I'm not sure what would be a large number here, but you would want a matching lower bound, right?
I want to say that first of all, that just there exists a constant that depends on beta, such that when you normalize this by log n, it converts the probability to this constant. Just is this right?
I see. Okay, so you want the tightness of the maximum of this divided by log n. At the first step.
Yes, at the first step, I'd like just to say that this divided by log n converges in probability to a constant. To a constant,
okay. No, the answer is that I don't think we can do that with our technique because as you see here, we are still far from, I think in reality, there is no 2 here. And we have the 2 because we would need the vortices to be very ergodic in a way. I think they are, but we don't have that. So we are still this factor of 2 off from the true maximum of the field. And
but
so
some constant. You know, there exists a constant such that you don't have to.
No. I understand, but to prove that there is such a constant, it would be more something playing with the techniques of Biscup and Louis-d'Or, or to try to understand locally how the max of an integer value Gaussian free field looks, or techniques like that, not quite the global techniques that we have. I see what is your question, but I think there is no way to apply our techniques. Mm-hmm. But it's a good question. I agree. In your low temperature case, you have ±1 fluctuations, so you're in a very good setting for this.
Yeah.
There was one question in the chat. How about the non-Abelian cases, such as SU2, I guess, in reference to what you said towards the end?
Yeah. So So this is of course very interesting. But if you go to the non-abelian world, the conjecture in dimension 2 is let me take the most appropriate slide, maybe this one. In dimension 2, if you would take a non-abelian group on the vertices here, the conjecture is that the 2-point correlation function is always exponentially decaying, always, whatever beta is. And the analog in lattice gauge theory is that this Wilson observable would always be smaller than exponential minus a constant times the area. So in some sense, when you go to the non-abelian case, you never cross this KT transition. You always stay in this exponentially decaying world. And of course, those techniques cannot say anything. Let me just say maybe one interesting remark in that direction, which is that if you do this story in dimension 3, our technique would give some impact of the vortices. They would improve on the McBride-Spencer bond on the vortices. But for the integer valued Gaussian free field, it is known by a deep work of Gup-Mert-Mac. I think I'm screwing a little bit the names, but Gup-Mert-Mac, I think. Anyway, so it's known that there is exponential decay of correlation always through the very small temperature. And our proof would only give tiny corrections of the vortices. And the reason for that is that in our proof, at some point in that case, we would not control well enough the quench disorder here. So even in some abelian cases in other dimensions than 2 and 4, our technique is not good enough for those behaviors. So not to mention the non-abelian case.
For the 3-dimensional case, you actually mean vortex loops?
So in 3-dimension, so in 3-dimension, it depends if you consider the Villain model in 3-dimension or if you consider the lattice gauge theory in 3-dimension. The vortices would not be the same for the Villain, in which case the vortices would be on the 2 forms, and for the lattice gauge theory, they would be on the 3 forms, and I think the loops would be for the Villain in that case.
So you cannot say anything about the XY model in 3-dimension? What type of a topological excitation it has?
In 3-dimension, we could say things, but that would not be. They would not even go to the 2-point correlation function that Dario and Vu have been doing. So, for example, I think the technique of Dario and Vu would not work in dimension 2, at least at the moment, because of the homogenization. And our technique do not work well when the green function is not blowing up, if you wish. So it would give things for integrating the XY model against a large-scale test function, but not the 2 points.
Well, I just want to make a comment that I think in the physics literature, at least, you only hear about vortex loops in 3-dimension.
Mm-hmm.
If you have periodic boundary condition and you don't have a vortex going around the whole system, all you have are loops which are actually not topologically stable because you can shrink them to 0.
Mm-hmm.
So it's comparable maybe to the vortex pair in 2-dimension.
Yeah, that's correct. That's the same thing. Yeah, that's the analog. This was done by Guth actually in 1980.
Okay.
And we did some work after that, but yes, the analog is vortex loops for the XY model in 3 dimensions.
Okay.
Yes, in some sense, the vortices they are naturally this Q equals dm, and m for the XY lives on the 1 forms, and the m for the lattice gauge theory lives on the 2 forms. So it tells you exactly where the vortices should live. But I should say that the name vortex is a bit misleading sometimes in the literature, because for the discrete groups, vortices lives in the forms just before. So in Chatterjee's work, vortices are not all vortices, for example. So it can be sometimes confusing.
More questions?
I have just one more question.
Mhm.
Yes, in the BKT transition, I
Yes.
see there is a exponent CT.
Where would that be? At the beginning, or?
Yes, there is a exponent in the exponential factor. There is exponent CT of the mass dimension.
Yes, yes.
And
This one?
how does this come? Where does this come from? Like, is there any parameter? Is there any parameter of mass dimension in the theory, or from which this mass comes?
Okay. So I don't know if this. Yes. So this is a hint of a massive behavior. If you want to prove what is a CT, to have bonds on what is CT, you can do cluster expansions, or you can also do Markov chain that quickly forget about what you had at the boundary. But now I guess there are very interesting questions that I'm not very well aware of. I know that Tom in the audience is, which would be how does CT behaves as a function of T, I guess, near the phase transition, because CT would need to drop to 0 before going to the power law decaying world. And I guess the way it behaves as T minus TC is interesting, probably related to the C infinity phase transition, but I'm not very knowledgeable on what's the behavior of CT when you get close to the transition. But far from the transition, it's very easy to get reasonable bonds on this constant C of T. So of course, those reasonable bonds, they will break before the actual phase transition. Otherwise, you would have a way to compute T BKT, and you don't. But
Okay, thank you.
thank you.
More questions? Okay, if not, let's thank Christophe for this really great talk.
Thank you.